Good day. Welcome to the workshop on building optimization-based multi-period planning models, sponsored by LINDO Systems. My name is Linus Schrage. Let's get started. So, usually when you're going to talk about a topic, you like to motivate folks that it's an important topic. So let's make our attempt at that by listing a good half dozen different situations where multi-period planning with optimization has been used with a fair amount of success. They range from supply chain planning models, where you're concerned about what should produce where, when, and shipped where and when. Financial models, where you're concerned with how your portfolio grows over time. Electricity generation problems, where you're concerned about which generators should be started in which periods. Natural gas distribution, where you're concerned about where to buy gas, where to store gas in preparation for a heating season. Resource extraction in oil fields, coal mines, precious metal mines. These three here, electricity generation, natural gas distribution, and resource extraction, share a common feature of you may have sufficient capacity long-term, but you may not be able to respond quickly to a sudden spurt in demand. So good planning is important there. Another application is scheduling of various sorts, staff scheduling in particular in healthcare, routing problems, particularly where there are time windows, you're routing over time, and population models of various sorts, such as in forest management, management of products like cheese and wine, where they gain value the longer you store them. And so there's an interesting trade-off decision to be made there. Some basic ideas, two concepts to keep in mind. Concept is perhaps too fancy a term for a planning horizon and a period. So a planning horizon, say in the petroleum industry, might be 20 years. The period length might be 1 year. And so you've got decisions of what should be done in each period, but taking into account that there are connections between the periods, there are going to be constraints connecting the periods. And so you have to worry about that also. So there's some design decisions of what should be the planning horizon, what should be the length of the period. We won't cover that in this presentation, but there is a longer presentation that's available that covers those topics. A little bit about the outline. We'll say a little bit about LINDO Systems and what special features there are in our software for handling time-based planning. A little bit about the history of multi-period planning. The basic inventory equation, which sort of underlies all multi-period models. How to present results. And a little bit about the two most common constraint types that you encounter in multi-period planning models, resource constraints and precedence constraints. Resource constraints on how much you can do of what in a period, precedence constraints constraining you when you can start doing something. This is a short presentation of a much longer presentation that's available. See the LINDO website if you'd like to see that longer presentation. A little bit about the software products from LINDO Systems. There are essentially 3 products plus from it. Underlying everything is a solver engine called the LINDO API. And it's quite general purpose. And sitting on top of that, you have a choice of either the What's Best spreadsheet add-in if you like to work in spreadsheets, or the LINGO modeling language if your models tend to be a bit more complex, multidimensional, so forth. We have a big library of application models available on top of that. So if you're developing a customized system, we've got off-the-shelf models, as it were, for supply chain, routing, vehicle routing, cutting stock problems. So for example, our cutting stock application has been running for 30 years. Not that its solve time takes 30 years, but rather that it's been in use very successfully in industry-leading companies in the country. In terms of features, talk mainly about the LINDO API. The most notable feature of LINDO API is comprehensiveness. It has everything you might want, from linear programming capabilities to solve large million variable problems to quadratic constraints, convex or non-convex, semi-definite programs, conic programs, nonlinear models of various sorts, non-convex or not. For non-convex models, we have the global solver, which can find guaranteed global optima for your non-convex problems. If you've got uncertainty in your model, that's a key thing. We have a stochastic programming capability to handle that, and you can have integer variables everywhere in the model. So LINGO sits on top of that. If you want an algebraic modeling language, what's best is a possibility if you want to have spreadsheets. Now, we have interfaces to the LINDO API from lots of different places, any sort of modeling situation. Perhaps the longest one is the GAMS modeling system. So that if you want to use GAMS, that's available. Or if you happen to be an AMPLE user, there is an AMPLE interface that's available. So lots of different interfaces available for it. A little bit about the history. Everyone likes to say, well, you know, the history of my topic goes back to biblical times. The same thing is true for multi-period planning. There's a story of the Joseph and the Pharaoh. Pharaoh had the dream about 7 fat years followed by 7 lean years. Asked Joseph what to do. Joseph's advice was use multi-period planning, build up inventories of grain during the fat years, and so you'll be okay during the lean years. That was great advice. The Pharaoh was happy. And the Pharaoh said, Joseph, how did you know what approach to use? And we all know the answer. Wait for it. He said, I used linear programming. So the first example of optimization being used for multi-period planning. A little bit more recent from that, there is a somewhat famous paper by Holt, Modigliani, Muth, and Simon, where they did some work for a Pittsburgh paint company, innovatively named the Pittsburgh Paint Company. It's a good, nice, simple introduction to the ideas of multi-period planning. They did a lot of aggregation. There was one aggregate product simply called paint. The workforce was aggregated, just a simple one kind of workforce. And the horizon length was 12 months. The period length was 1 month. So the question was, what should we do in each one of these 12 months, taking into account the interaction between months? There were essentially 3 decisions you could make in the month. Should I increase or decrease the workforce level? Should I resort to overtime? And then indirectly, should I use inventory to build up inventory like Joseph did for the Pharaoh to be prepared for future periods? Hansman and Hess in 1960 gave a linear programming based approach for tackling this paint company aggregate planning model. And the basic equations in that model are as follows. And I'd like you to sort of pay attention to the first 2. There is the so-called inventory equation, simply saying that the inventory at the end of one period is equal to the inventory at the end of the previous period, plus what came in and what went out. And so that's the general inventory balance equation, which is key or crucial to all of these multi-period planning models. Workforce is modeled in exactly the same way as an inventory. The inventory of workforce that you have at the end of period T is equal to the inventory of workforce at T minus 1 plus what you hired, brought in, plus went out. And then within each period, there are various capacity constraints. Here, there's a production capacity constraint on that the amount that you produce in T is limited by what your workforce level is and how much overtime you have. And they allowed inventory to be positive or negative, allowing backlogging if you wished. And the objective was simply to minimize all of the costs involved, including the cost of regular workforce, the cost of overtime, the cost of hiring, the cost of firing, the cost of positive inventory, and the cost of negative inventory. So the general structure now, let's review the bidding here. The general structure is you're going to have an inventory variable for each commodity type that's in your system. So we'll call that for commodity C in time period T. And then you'll have this inventory material balance constraint for every commodity for every time period in your system, which simply says that the stuff that came in, the beginning inventory plus arrivals, must be equal to what you shipped out and the ending inventory. So that's the basic inventory equation, which is sort of crucial to understanding multi-period planning models. Now, let's talk a little bit about displaying results, and this happens to be a useful, important thing. And so let's talk about a specific problem, a jet taxi routing problem, which you can also think of as a full truckload load selection problem. So we have to figure out which flights to cover, which flights to fly, of a number of flights that people would like to fly. So these might be for private business flights. And so the basic inventory constraint for this is going to be that the aircraft at a particular city at a particular point in time, in a particular period T, is going to be equal to the aircraft at that city the previous period, plus what came in, minus what went out. And your decision variables are going to be this, what went out. You're going to decide, should I fly this flight or not? And that will be based on various kinds of profit considerations. So here's a little example. So it involves 7 cities with various data associated with them, various cost and profit related data associated with them. And here is the complete detail of this problem. So we've got 9 flights that are being available to cover. And the question is, which of these 9 flights should we as a taxi service decide to cover? So for example, there's a flight, someone wants to fly from Los Angeles to Salt Lake City on May 5th at 10 in the morning. And if we took that one, that might be useful. And because somewhat later, there's a flight from Salt Lake City to Phoenix here on the 6th at 2 p.m. there. So we might fly to Phoenix. And if we went to Phoenix on the 7th, there's a flight from Phoenix to Chicago. So you can sort of see that how we might cover some of these flights with our airplane. And so we might ask questions, how many airplanes should we have to cover these 9 flights? What could we do with 1 airplane? What could we do with 2? Well, you would need travel time information. So that's down here. Here are the travel times between the various cities. So this is the complete data for that problem. It's not real easy to get a handle on this problem just looking at it in tabular form. So let's look at some graphical ways of trying to understand these multi-period planning problems. And so I'll mention 2 things. One is space-time diagrams. Other is Gantt charts. And then also available in LINGO, besides these 2 chart types, is time conversion routines that in the previous slide, we saw that the times were stated in day, month, hour kind of notation, whereas when we're doing modeling, we like to work with scalar single variable time. So LINGO has routines for doing that. So here is a time-space diagram for the 9 offered flights, or the 9 flights that might be available. And this gives you a little bit better understanding, I think. So for example, at the start, there's a flight from Los Angeles to Salt Lake City. And so if we did that flight, we could then next fly from Salt Lake City to Phoenix. And if we were at Phoenix, we could next fly from Phoenix to Chicago. And from Chicago, we could stay on the ground for a bit and fly to Phoenix again. And then there wouldn't be much we could do at Phoenix, although we could reposition. If we were willing to do a repositioning flight from Phoenix to Salt Lake City, we could then cover that flight there. Or if we did the repositioning flight to Salt Lake City and waited here, we could fly from Salt Lake City to Las Vegas and then back from Las Vegas to Salt Lake City. So I think a time-space diagram does give you a better feel for what the problem is. And it's quite easy to generate a space-time diagram in LINGO. There's a simple command, chart space time, and which will throw up a chart like this. let's look at what we can do with one aircraft. So if we have one aircraft and are willing to do some repositioning, here's what happens. So we fly from Los Angeles to Salt Lake City, stay on the ground for a bit, fly from Salt Lake City to Phoenix, Phoenix to Chicago, Chicago to Phoenix again, do a repositioning flight back to Salt Lake City, fly to Los Angeles, repositioning flight to Salt Lake City, back to Las Vegas, Las Vegas, back to Salt Lake City. And so with one aircraft, we could cover 7 of those 9 flights. How many flights could you cover if you had 2 aircraft? It looks like you can do all of them. So again, you just have to do 3 repositioning flights and we've covered all of them. So, and the decision to do the repositioning flights will depend upon the costs and profits, the cost of a repositioning flight and the profit of the loaded flight that we gain as a result of doing that repositioning. So similar models are done by the airlines when they are trying to come up with a schedule, a weekly schedule or a monthly schedule. So here is the solution for the one aircraft version of the problem. And so up in the first section are the loaded flights that we fly, and in the bottom section are the 2 repositioning flights that we fly. And notice that we output the results in year, month, day, hour, minute, day of the week, time, and this is all in local time for these cities. And so how do we sort of do that easily? Well, it turns out that's quite easy to do in LINGO. LINGO has 2 routines for moving back and forth between what we would call calendar time, year, month, day, hour, minute, second time, and internal scalar time, which is just a single scalar variable. So you like to work with a scalar variable when you're, say, computing the arrival time at Phoenix. If I'm leaving from Chicago at a given time and I know what the travel time is from Chicago to Phoenix, I just want to add on the travel time to get my arrival time at Phoenix. So if I start at Chicago and I know the year, month, day, hour, I can use this routine to get the scalar time for that flight. Essentially, you can think of it as GMT, Greenwich Mean Time, and then add on the travel time. That gets me to Phoenix, and then I can do the conversion the other way to write out what year, month, day, hour, and minute does the flight occur. So both of these are fairly simple routines or functions, quite easy to use, both the calendar routines and the space-time chart routine. So this is how you generate that diagram that we just saw previously, that command. Now, let's talk about some other constraints. So you can think of it as there are basically 3 kinds of constraints in a multi-period planning model. You've got the basic inventory constraint, which ties periods together. Then within a period, you probably have resource constraints that say there's a limit to how much you can do, how many flights you can have in the air at once, depending upon how many aircraft I have, things like that. And then the precedence constraints, which are, again, sort of between periods, but they limit which activities you can do based on which activities you've already done. To motivate precedence constraints, let's talk about a couple of examples here. The common one is mining of various sorts. You can't remove a particular block until you've removed the blocks above it in a mine. In petroleum extraction, it's not quite so obvious, and we'll talk about that shortly. In air traffic congestion modeling, there's precedence constraints in terms of moving between various air sectors in a flight region that you're modeling. In process industries, manufacturing in general, you will have sort of job shop scheduling kinds of issues, precedence constraints that you can't put a batch of chemicals into tank J until it finishes step J-1. So those are examples of precedence constraints. Let's look at precedence constraints a little bit more closely. A good way to look at both precedence constraints and resource constraints at once is with a Gantt chart. So here's a Gantt chart for a problem, a job shop scheduling problem, where there are 6 jobs and there are precedence constraints among the activities in the job. And so let's look at, say, job 3 here, which is the blue one. The precedence constraints say I can't start the second operation on this blue job until the first one finishes, can't start the third one until the second operation finishes, can't start the fourth task until the third task finishes, so forth. So the precedence constraints are over time, saying which activities I can start when. The resource constraints are vertically in a graph like this. It simply says that if I sum over all activities on machine 3 in any time period, I can have at most one of them operating at once. So a Gantt chart is a good way of seeing precedence constraints going horizontally and resource constraints going vertically in the problem. Now let's look at the mining example a little bit more closely and how precedence constraints arise there. So here we have a little 2-dimensional mine, and we've got the mining opportunities divided into 14 different blocks, and the precedence conditions are that I cannot get at block 9 unless I have removed blocks 4 and 5 previously. So there's profit contributions of 10 associated with when I remove block 9, 10 with 11 and 12, and 1,000 when I remove block 13. So there are precedence constraints among the blocks. And here we state that there's a resource constraint that we can only remove 2 blocks per year. So that's true in any sort of extraction kind of business, that you've got a limit on how many rigs you have to do the extraction, and that puts us a constraint there. In terms of objective functions, you could imagine that if you wanted a fairly continuous stream of revenue, you would tend to remove blocks along the right here. So you'd get the 10 fairly early, get the next 10 fairly early, so forth, finally get the 1,000 there. If you had a different kind of discount factor, you might say, this $1,000 is really the important thing, and you might remove blocks from the left first and not get any real money until you get this 1,000 down there. So good example of precedence constraints in the mining extraction example. Now let's look at how we represent precedence constraints, and I will suggest to you, probably shouldn't call it a trick, but a convenient way to represent precedence constraints. So we will represent precedences by precedence pairs. So the pair ij says that j cannot be started until I has completed. And we will generally have a 0-1 decision variable, zjt, which will be 1 if block j, or more generally if task j, is started in period t. So those will be the fundamental decision variables. Do I start this activity in this time period? And then the crucial constraints for the precedence constraints are that if I want to start activity j in period t, then for all of its predecessors I had to do them in some previous period, and could be current period if I can do them simultaneously, but otherwise a previous period. So that's the introduction to precedence constraints. Now let's look at that a little bit more carefully. So the general approach is, for these decision over time problems, you'll have a ZJP variable, which is 1 if task J is started in period P, else 0. And then the precedence constraints simply say that if we start task J in period P or earlier, we had to start task I in period P or earlier also. Now, here is sort of the trick. If you want to call it a trick, it's convenient to define a cumulative done variable, WIP, which is equal to 1 if task I was started in period P or earlier. And so it's simply the sum of these, did I start in P, or did I start in P minus 1, or did I start there? And you can write it recursively. It's fairly simple. WIP is simply equal to WIP minus 1 plus the start variable here. So this is a constraint that will actually appear in the model. Then the precedence constraints are quite easy. If I must precede J, you simply say WJP must be less than or equal to WIP, which means I must have been started at least as early as J. And if there's a time lag or a processing time associated with activity I or task I of lambda, it simply gets added on to that lag right there. And the precedence constraint has this fairly simple fashion right there. So precedence constraints are fairly simple if you define this cumulative done variable. Now, another example of precedence constraints is in petroleum extraction in oil fields. The production curve for an oil well typically is represented by 2 or 3 or 4 stages. It's fairly constant early in life, and then the production starts to decline. And you may have to do all kinds of sorts of things to the oil wells to get it to continue producing. And so you have precedences between these various stages. You don't start the second stage until you have completed the first stage. You don't start the third stage until you've completed the first stage. And for the oil field extraction problem, there's an additional slight complication that there are these production variables of what the actual production is, and you have to connect them to the did I start this stage or not variable or not. And it's a fairly straightforward connection, which you can look at in your leisure if you review this presentation later. But it's fairly easy to do this linkage. Now, let's look at resource constraints. And again, we said there's this slight trick for precedence constraints. There's also a slight trick for resource constraints. And for resource constraints, the important thing is to do things in discrete time. And so the basic idea here is you want to decide, what can I do in a particular time period? You're going to have a constraint of what you can do in that time period. So let's look at that more specifically. You will have for each time period, for each machine, you will have a constraint that at most one task can be assigned to a specific machine in that time period. And you may have additional constraints that tasks can be done no earlier than its starting time window, no later than its due date. And there may be values associated with assigning various tasks to different machines. So for the task to machine assignment problem, lots of examples of it are assigning airplanes to parallel runways, which runway should it get, or which gate should an aircraft get at a terminal, which de-icing station should it get at a northern airport. If it's trucks we're dealing with or ships, which truck should be assigned to which dock in each time period. If it's a hotel, it's which hotel guests get assigned to which hotel rooms in which day. Planning period is a day typically in hotels. If it's hospitals, assigning surgical procedures to operating rooms, so forth. And you have the resource constraints that each resource can handle at most one task at a time. So an example of the importance of sort of doing these resource constraints the right way is there's a textbook way of representing resource constraints, which is usually done in a so-called either or kind of way, that if I and J tasks use the same machine, the textbook way says, well, there's a constraint that says either I has to precede J or either J has to precede I. That's an easy way to describe it. It's not a very useful way computationally. You want to use the discrete time approach to do it computationally. And so for a 20 task assignment problem on one machine, if you do it with the textbook big M so-called formulation, it takes 60 seconds well over to solve. If you use the discrete time formulation, it solves in 1 second. A real problem involving assigning 55 aircraft with time windows to 12 gates at a terminal, the discrete time formulation takes 1 second. Who knows how long the continuous time formulation would take to solve a problem that large. So, in conclusion, in our limited time here, this is a very abbreviated presentation of a much longer one that's available on the web at lindo.com. Simply search in the models library here, keyword multi-period, and it will cover a host of other important topics in multi-period planning. So if you're going to get involved in multi-period planning, I recommend that you look at all of these issues, all of these considerations, and take them into account. So that concludes things. Thank you very much for attending. Hope to hear from you.